All right, let's jump right into this explainer where we are going to completely demystify how to connect your Keil software code with a Proteus hardware simulation step by step. If you're a beginner looking to bridge that gap between typing lines of code and actually seeing them run on a simulated physical circuit, well, you're in the exact right place. We're going to break this whole integration down so you can seamlessly test out those microcontroller projects before you ever have to touch a real breadboard.
So, here is our roadmap for today. We'll start by meeting Keil and Proteus, then move on to writing the microcontroller code, generating the hex file, building the Proteus schematic, linking the software to the hardware, and finally tackling the final simulation challenge.
Okay, Section 1. Meet Keil and Proteus.
I want you to think of Keil and Proteus as two completely separate islands, right? We desperately need to connect them for our project to actually work. To paint a clearer picture here, Keil is our software island. This is your environment where you'll be writing your C programming specifically for an 8501 microcontroller, like the 89C52 series. Proteus, on the flip side, is our hardware island. It's this super powerful PCB design and circuit simulation software where we assemble the virtual components. Now, when we successfully combine these two, we get a fully functional simulation. The catch? They don't just talk to each other automatically.
Because they don't talk automatically, we can't just drag and drop raw C code directly over into Proteus. We have to build a bridge. And that bridge is the hex file. It's a compiled version of your code that the Proteus microcontroller can actually understand and execute. Honestly, building this hex file bridge is the absolute core of making these two distinct programs handshake and communicate with each other.
Moving right along, Section 2, writing the microcontroller code. Take a look at this. This is a beautifully simple C program written in Keil, designed to do one thing: blink a single LED. Notice that little S-bit declaration up at the very top? All that's doing is assigning the LED to pin 0 of port 2. Then, down inside our main function, we have an infinite while loop. This loop forces that exact pin to alternate between low and high, so 0 and 1, calling a 500 millisecond delay function right between each state change. It's simple, it's elegant, and it's absolutely perfect for our first simulation run.
But hey, before we go through all the trouble of building that bridge to Proteus, we can actually verify that our code logic works right here on the software island. By popping open Keil's debug window and turning on the peripherals window for port 2, we can simulate the microcontroller's internal state. When you click Run, you should physically see bit 0 of port 2 alternating between high and low right there on your screen. It's an awesome little sanity check just to make absolutely sure your software foundation is rock solid.
All right, Section 3, generating the hex file.
This is it, the most critical part of setting up our software links. Let's look at the exact steps you need to follow so you don't get lost in all the menus. It's a pretty quick 4-step process. First up, you right-click on Target 1 over in your project tree. Second, navigate to the Output tab. Third, enable the specific checkbox to create the hex file. And fourth, you rebuild the project. Let's break that down visually. Look really closely at this tiny, easily missed checkbox. When you open the Options for Target window and click that Output tab, you're going to see a box labeled Create Hex File. By default, this is usually unchecked, and let me tell you, forgetting this is practically a rite of passage for beginners. You literally must check this box and make sure the hex format is set to hex 80. Because if you skip this, Keil will gladly compile your code, but it won't generate the actual file Proteus needs. Your bridge will be missing. Okay, so once you've checked that box, hit the Rebuild button. Down in the Build Output window at the bottom of your Keil interface, you are looking for this lovely success message. It'll explicitly say creating hex file, and fingers crossed, it ends with 0 errors. This is your confirmation that the software side of your bridge has been built flawlessly. So, where did that file actually go? Well, if you open your project folder in Windows Explorer, look for a folder named Objects. Inside there is where your brand new hex file is hanging out. Make a mental note of exactly where this Objects folder is located on your PC, because we're going to need to point Proteus directly to it very, very soon. Let's move on to Section 4, building the Proteus schematic. First things first, create a new project in Proteus and just set the schematic to default. We don't need to worry about a PCB layout for this explainer. Now, before we start wiring anything up, we need to gather our virtual components. Using the P button, that's the picker button on the Devices toolbar, you're going to search for these exact items: an AT89C51 or AT89C52 microcontroller, a push button, two 33 picofarad capacitors, a crystal oscillator, your LED, and finally,
a 470 ohm resistor. Got your parts? Awesome. Now, carefully arrange and wire them to match this schematic exactly. You want to place that 8051 microcontroller smack in the center of your sheet. It's the brain of the whole operation. See how the crystal oscillator and those two capacitors are wired to pins 18 and 19? That provides the clock signal. Then over on the right, at pin 21, which remember corresponds to port 2 pin 0 from our Keil code, we've got the LED wired in series with a 470 ohm resistor going right to ground. Section 5, linking software to hardware. All right, we are finally ready for the ultimate handshake. To establish this link, grab your mouse, head over to Proteus, and just double-click directly on the 8051 microcontroller in your schematic. Boom! That opens up the Edit Component window. This window right here is the Magic Control Center, where you tell the virtual microcontroller exactly how it ought to behave. Inside that Edit Component window, scan down until you find the field labeled Program File. See the little yellow folder icon sitting next to it? Click it. Now you just navigate your computer's files back to that Keil objects folder we talked about a minute ago. Select your compiled hex file, and just like that, you are officially downloading your Keil software into your Proteus hardware. You've linked the islands, hit OK, and you're set. And that brings us to Section 6, the final simulation challenge. To see all your hard work pay off, glance down at the very bottom left corner of the Proteus window. You'll see some playback controls. Go ahead and click the Run Simulation Play button. The instant you do, the Proteus engine starts reading the instructions straight from your Keil hex file, and you are going to see that virtual LED on pin 21 start blinking on and off every 500 milliseconds, just like we coded. It is honestly so satisfying to watch that software logic spring to life as hardware action. So, now that you've got this basic setup completely mastered, and you know exactly how to generate and link that super important hex file, I am going to leave you with a fun little lab challenge. Can you take everything we just went over, expand your Proteus schematic to include 8 individual LEDs, and tweak your Keil C code to make them run in a sequence from left to right? Think about it. You've got all the foundational tools you need to build the software, wire up the hardware, and bridge them together. Good luck with the challenge, keep tinkering, and as always, happy coding.